In this video, we're going to learn about functions. And I'm going to use the relations from the previous video to describe a couple of functions. Let's start with the definition of a function. So function is a relation where each element in the domain is paired with exactly one element in the range. Exactly one being the key. So in other words, you could say each x, if x was the domain, has only one y, whereas the y values are the range. So let's look at our first example. This first example is a function. That's because each x value, so each element in the domain, is paired with exactly one element in the range. This one's pretty straightforward. Each x has a separate y value. Looking at our next relation, this too is a function. That's because each x has only one y. And this may be a little confusing because here you have two x's, so two values in the domain, -3 and 0, both paired with the same value in the range. This is still a function though, because even though this y value is the same, -3 is only paired to the 2. It's not paired to anything else. And 0 is only paired to the 2. It's not paired with anything else. So you can have multiple arrows pointing in to the same value of the range on a mapping diagram, but when looking at the domain, you can only have one single line coming out of each of the values. So the first relation is a function. The second relation is a function. So I'll just say function and function. Let's look at this third example. Right off the bat, we can see that this is not a function. But why is that? Remember, each x has only one y. And here we have the value of -2 in the domain paired with two separate y's. Therefore, it's not a function. This value -2 was paired with the 1, and it was paired with the 2. There's two lines coming out of this value in the domain. Therefore, it's not a function. Leaving these examples up, I'm going to give you a definition of a special function. So a one-to-one function, first off, is a function itself. So that means each x, so each value in the domain, is paired with only one y value, or value in the range. Also, for it to be a one-to-one function, each element in the range is paired with exactly one element in the domain. So not only is the domain paired with one element in the range, but the range is paired with one element in the domain. So there's one example up above where this case is true, and that's the first relation. This first example is a one-to-one function because you can see each x goes to one single y value. This is not a function at all, so we can't even consider this to be a one-to-one function. This middle function is not a one-to-one function because we have two x values mapped to the same y value. One-to-one, each value is distinct. Now let's move on to looking at not just ordered pairs as functions, but equations as functions. So, when an equation is a function, we can say that x's are the independent variable and y's are the dependent variable. That means as we change x, y is going to change accordingly. So in function notation, the way you would write it is that f parentheses with an x inside replaces y. This is read as f of x, or the function of x. So the function of x replaces y. So let's look at a few examples where we're going to use f of x in the case of y. Here I have three different examples of equations. We're going to plug in values for x, solve for y, and then we're going to see which of these equations are functions. We'll also go over the domain and range of each function for practice. On my coordinate plane, I'm counting by 2's. So our first problem, let's say I pick a positive 4. 3 times 4 is 12. 12 plus 1 is 13. So we're going to have 4, 13. So going over 4 in the x and 13 in the y. Let's go ahead and plug in negative 2. When we plug in negative 2 for x, negative 2 times 3 gives us negative 6. Negative 6 plus 1 would give us a negative 5. So y is negative 5 and x is negative 2. So negative 2, negative 5. So negative 2 down to negative 5, and then we're going to connect the line. And this line isn't going to be perfectly accurate since I drew this coordinate system, so I recommend using graph paper when you're doing it yourself. But this suits our needs for now. So this is our first equation. The domain, x, look, it goes infinitely to the left, and x continues infinitely to the right. So the domain is all real numbers, and this is our symbol for all real. The range also continues down, because this arrow is showing that it's going to keep moving this way, and that arrow is going to keep moving in that direction. So it's not just going to keep going to the right, but it's also going to continually go up. So the range is also all real numbers. We also can see that for each x value, we're only going to have one y value. So each element in the domain is paired with exactly one element in the range. So this indeed is a function. Let's go ahead and write this in function notation. Instead of y equals 3x plus 1, remember that f of x replaces y. So that's going to be the function of x equals 3x plus 1. And we would plot this function the same way we plotted the equation. We would plug numbers in for x and solve for that function of x. So if we plug the 0 in, we would still get that f of x is equal to 1. So when an equation is a function, you can think of the y-axis as the f of x axis. But we're going to graph these other two equations on here, and we don't know if they're functions yet. So let's just keep this as the y-axis. This next one's fairly simple. It's dealing with absolute value. So it says y equals the absolute value of x. So we know that y is always going to be positive. So we can plot 0, 0. When x is 4, y is positive 4. When x is negative 4, y is still positive 4. And you can do the same for 8. Negative 8, the absolute value of negative 8 is positive 8. The absolute value of positive 8 is positive 8, and so on. So this equation will actually make a V shape. That means the domain, x can continue on in the left, and it can continue on in the right. So the domain is the set of all real numbers. But let's look at the range. Since it's the absolute value, we never get into the negative values for y. So the range is greater than or equal to 0. So y has to be greater than or equal to 0, and that's the range. We could also write that in interval notation, which would be 0, comma, positive infinity. This is also a function because each value in the domain is paired with exactly one value in the range. Although the values in the range are repeated, for example, we have negative 8 and 8 both pair with a positive 8, this is still a function, but it isn't a one-to-one function like our previous example was. But it's still a function, so let's write that in function notation. We're going to replace y with f of x. So f of x equals the absolute value of x. Now, let's look at our last equation. Y equals the square root of x. So when x is 0, y is 0. When x is 8, y is slightly less than 3. However, think about it this way. We're saying that y squared is equal to x. That means y can have a positive or a negative value, and when you square it, it's going to give you the same exact value. So that 2.83 squared gives us 8, but a negative 2.83 squared also gives us 8. Let's look at 4. If y is 4, 4 squared gives us 16. So when x is 16, the square root of 16 is 4. But remember that negative 4 squared is also 16. Connecting those dots, this isn't going to be a V shape. It's actually going to be more like a sideways U. So the domain, x is only ever positive. So x is greater than or equal to 0. In interval notation, that would be 0, comma, infinity. Looking at the range, y can go on infinitely in the positive direction, and it can go on infinitely in the negative direction. So the range is all real numbers. Think if we had that x was 64. That would be 8 squared or negative 8 squared. Going to a higher value, we could have 100 squared or negative 100 squared, and so on. However, this equation is not a function. That's because, remember, for this 8 value that we plotted, we had a positive 2.83 and a negative 2.83. So here we have one x value, which was 8, paired with 2 separate y values. So this is not a function. But when we graph it out, there's an easier way to see whether an equation is a function or not that doesn't involve looking at each individual point. And that's with the vertical line test. If a vertical line intersects an equation at more than one point, then that equation is not a function. And that vertical line could be drawn absolutely anywhere along the coordinate system. So, for a function to pass the vertical line test, it can only intersect at one point or less than one point. Let's go ahead and draw a vertical line. Remember, the red line was a function, and it passes the vertical line test. It only intersects at one point. The blue line was also a function, and this also only intersects at one point. However, the green was not a function, and you can see that it intersects at 2 separate points. So the green equation would not pass the vertical line test, and therefore is not a function. And the vertical line test has to hold true all over the graph. So you can see if this marker was my vertical line, as I move it, it's still only intersecting the blue and red once, but it begins intersecting the green at multiple different points. And that is a quick introduction to what a function is.